Hi folks! The following video talks about two final reactions of alkenes known as Syn-Dihydroxylation and ozonolysis. We've previously seen a reaction known as anti-dihydroxylation, where recall dihydroxylation refers to the addition of two alcohol OH groups across an alkene. For anti-dihydroxylation, the first step is treatment of the alkene with a peroxy acid, RCO3H. This generates an epoxide, a three-membered ring featuring an oxygen. Treatment of the epoxide with water under acidic conditions generates the dihydroxylated product. The OH groups in anti-dihydroxylation add from opposite faces of the alkene, so one is shown as a wedge and the other one is shown as a dash in each of these cases. You could describe the alcohol groups as being at positions 1 and 2 relative to each other, so these products could be called anti-1,2 diols, where di is for 2 and ol is the alcohol suffix. It's also possible to perform syn-dihydroxylation reactions in which the two OH groups add to the same face of the alkene. You don't need to know the mechanism for these reactions. One syn-dihydroxylation method is treatment of an alkene with osmium tetroxide, OSO4. You don't need to know the mechanism for how this occurs, but this has the effect of adding two oxygens from osmium to the carbons of the alkene to generate two new carbon-oxygen bonds. The oxygens add to the same face of the alkene, so both of these new carbon-oxygen bonds could be drawn as wedges, or they could both be drawn as dashes. The oxygen remains attached in an intermediate known as an osmate ester. To remove the osmium and replace it with a hydrogen on each oxygen, there are two different possible conditions in a second step. One is treatment with Na2SO3 and water, or you can treat the osmate ester with NaHSO3 and water. They have the same effect. Each set of reagents will cleave the osmium-oxygen single bonds of the osmate ester and replace the osmium with a hydrogen on each oxygen. The second step generates that syn-dihydroxylated product. The alcohols are at positions 1 and 2 relative to each other, so we could describe this as a syn-1,2 diol. Although this syn-dihydroxylation method works really well, there are a couple of downsides. These are that osmium tetroxide is toxic and very expensive. One alternative reaction you'll see in the textbook is to use osmium tetroxide but add a co-oxidant. This allows you to use catalytic amounts of osmium tetroxide instead of stoichiometric large quantities of it. Some co-oxidant examples you'll see are NMO, featuring a nitrogen-oxygen bond where this oxygen is quite reactive, or a reactant called tert-butyl hydroperoxide. So instead of the two-step method I showed on the previous page, you could treat the alkene with catalytic amounts of osmium tetroxide with NMO present in the same step, or with tert-butyl hydroperoxide present in the same step, and this would be a one-step method to get the syn-dihydroxylation. In the product in each case, I would draw both OH groups added as wedges, or draw them both as dashes. In this case, those are the same molecules because we've generated a meso compound. A second alternative is getting rid of the osmium entirely and using potassium permanganate, KMnO4, under basic conditions instead. This reaction needs to be performed at low temperatures. What these syn-dihydroxylation conditions would look like is treatment of the alkene with KMnO4 and NaOH at a cold temperature in a single step. This is just another method of getting the syn-1,2-diol product. You don't need to know the mechanism, but in this case as well, you proceed by an intermediate featuring a ring of your carbons of the alkene and oxygens from manganese in a 5-membered ring. It is the generation of this intermediate that gives that syn addition selectivity. I want to show you some examples of Syn-Dihydroxylation reactions. Here I'm treating a substituted cyclic alkene with KMnO4 NaOH under cold conditions. These reaction conditions will add a new OH group to each of the carbons of the alkene. Here I've initially drawn the product without showing stereochemistry, and now I need to determine if I've generated any new chiral centers. These 2 carbons that had OH groups added to them are both new chiral centers. When this is the case, you need to show that syn addition of the OH groups has occurred. Here you would draw 2 products, one where both OH groups are dashed, and one where both OH groups are wedged. Notice that in these products, the methyl group is present either as a wedge or a dash. Now let's consider this cis-disubstituted alkene being treated with first osmium tetroxide and then second NaHSO3 and water. These are again just different syn-dihydroxylation conditions. I would first draw the product where I've added a new OH group to each of the carbons of the alkene. And in this case as well, I've generated 2 new chiral centers. Here I need to show syn addition, but rather than a mixture of 2 enantiomers, this reaction forms a single product. The reason this is the only product is that it is a meso compound. It has 2 chiral centers, but it has an internal plane of symmetry. Because it's a meso compound, it can't have an enantiomer, so it is the only product that forms. Last, let's consider a tri-substituted alkene being treated with catalytic amounts of osmium tetroxide with NMO present. First, without worrying about stereochemistry, I would add a new OH group to each carbon of the original alkene. Then I would identify that only 1 new chiral center has formed in this case. When this is the case, although syn addition did occur, you only need to worry about showing stereochemistry at the new chiral center. I would draw 2 products that are enantiomers of each other. One of these has the chiral center with an OH group as a wedge, and in the other one, this chiral center has a dashed OH group instead. The final reaction we'll discuss for alkenes is called ozonolysis. This is treatment of the alkene with ozone, O3, and it leads to complete cleavage of this carbon-carbon double bond, like both the sigma bond and the pi bond, and you form 2 new carbon-oxygen double bonds in the process. This reaction as well, you don't need to know the mechanism, you just need to know the reagents and be able to predict the products. What ozonolysis will look like for alkenes is you start out with your alkene and you treat it with reagents in 2 steps. First, you treat the alkene with ozone, and then in a second step, you treat your compound with DMS or zinc and water. Ozonolysis will completely cleave the carbon-carbon double bond of the alkene, and each carbon of the alkene will have a new double bond to an oxygen in the products. This ozonolysis would generate 2 products, where the left carbon of the alkene has a new double bond to an oxygen in this product, and the right carbon of the alkene has a new double bond to an oxygen in this other product. The reagents for ozonolysis are ozone, which features 3 oxygens in a row where you have positive and negative charges present, and DMS stands for dimethyl sulfide. This is a sulfur with 2 methyl groups. I want to show a few more examples of predicting the products for ozonolysis reactions. Here I'm treating a cyclic alkene with ozonolysis conditions. Step 1, treatment with ozone. Step 2, in this case, treatment with DMS. Ozonolysis will completely cleave the double bond of the alkene, and in its place, each carbon of the alkene will have a new double bond to an oxygen. When the alkene is in a ring, the ring gets opened up to form those carbon-oxygen double bonds. So these 2 carbons were originally the alkene. The alkene completely broke, and you have 2 new carbon-oxygen double bonds in its place. Here's another example, now featuring 2 alkenes, one in a ring and one off of the ring. The first step here is the same, treatment with ozone, but here I'm using the second step of zinc and water. This will have the same effect as DMS. Imagine completely cleaving the carbon-carbon double bonds of each alkene, and each carbon of the alkene is going to get a double bond to an oxygen. When the alkene of the ring breaks, you will open up the ring. So I'm opening up what was formerly an alkene between these 2 carbons, where each carbon gets a double bond to an oxygen. And then the other alkene will split into 2 different molecules. This carbon became this carbon in the product, and this carbon, which has 2 hydrogens attached to it, became a second aldehyde in the products. Here's just another example of 2 alkenes arranged in a ring in a different way. Here I'm showing the 2 steps of ozonolysis again. Imagine both of these alkenes breaking and being replaced with bonds to oxygens. In this case, because I'm splitting both alkenes in the ring, the whole molecule is going to split in half. Each carbon-carbon double bond is broken, and each of those carbons is now doubly bonded to an oxygen. In ozonolysis, I really recommend that you carefully check your number of carbons in the products. It's really easy to add or remove carbons when drawing these products. Alright, so today's video talked about 2 new types of alkene reactions. These were Syn-Dihydroxylations and ozonolysis reactions. You do not need to know the mechanisms for either of these reactions, but you do need to recognize the reagents, be able to provide the reagents if needed, or be able to predict the products. That's it for this video. I will see you in class.